Graphene. Everybody's talking about it. When hearing some of its basic properties, you might have wondered if people were confusing it with some kind of substance only found in comic books. It's 1 atom thick, conducts electricity better than silver, conducts heat better than diamond, and it's stronger than steel. It would take the focused force of an elephant balancing on a pencil point to pierce through a piece of graphene as thick as plastic wrap. And yet, graphite is made of the same stuff. And yeah, that crumbly stuff used to make your pencil is a lot less impressive. So what's up? Graphene is made of carbon, and carbon has only 2 naturally occurring crystalline structures. Graphite, which is just stacks and stacks of graphene piled on top of each other, and diamond, which is a network of carbon atoms arranged into tetrahedrons, one after the other. For being composed of entirely the same element, those 2 things don't seem to have a lot in common. Diamond is clear, graphite is black. Diamond is a nearly perfect electrical insulator, while graphite is both a great conductor of heat and electricity. The differences between these substances all come down to the arrangement of their atoms. Carbon has 4 outer electrons. In diamond, all 4 of those electrons bond to carbon atoms around it, forming those tetrahedrons. This makes for an extremely rigid and strong crystal. It's an insulator because there are no leftover electrons to carry a current, and it's clear because light can't easily excite electrons that are tied up in such stable bonds, which is where they'd otherwise be absorbed. Graphite, on the other hand, is a crystalline form of carbon in which each atom is only bonded to 3 other carbon atoms. Those atoms form a 2-dimensional sheet of hexagons in which each atom has 1 unpaired electron left over. And those electrons will go flying across the matrix of atoms if you apply an electric current, allowing it to readily conduct electricity. They also gobble up any photons coming their way, which is why graphite is black. But while graphite is a great conductor, its natural form consists of layers of those sheets. So if a current is applied to it, those free electrons have lots of different directions they can go in, taking tangents up and down and left, right, and so on. But if you strip away just a single layer, forming graphene, then you have what amounts to an electron superhighway, a flat matrix of carbon atoms for that current to fly across. And those sheets of carbon are pretty easy to separate because they're not molecularly bonded to each other. That's why graphite is so soft. Instead, they're held together by van der Waals bonds, kind of a weak electrostatic bond that's the same force that makes sticky tape sticky. And in fact, graphene was only discovered in 2004 when 2 physicists at the University of Manchester, Andrei Geim and Konstantin Novoselov, decided to use sticky tape to peel off thinner and thinner layers from a slab of graphite. Eventually, they got a layer just 1 atom thick. So that's what it is, but what is it good for? Because of its terrific conductive properties, scientists are excited by the possibility of using graphene as a replacement for silicon in microchips. Not only can electrons move faster across graphene, they're also subjected to less noise. That means the electron can move from one side of the sheet to the other in a straight line without detouring around a whole lot of atomic potholes. Scientists think that graphene transistors could operate at frequencies of up to 1,000 gigahertz. That's 10 times the maximum of silicon. Another proposed use for graphene is in touchscreens. The topmost layer of a touchscreen has to be an excellent conductor of electricity so the device can sense your fingertip. The material we use now is indium tin oxide, but it's both rare and brittle. Even ground into powder, graphene retains many of its extraordinary properties, so it could replace graphite or other forms of carbon in anything from car tires to AA batteries to make them stronger or more conductive. The biggest problem with graphene, though, is how hard it is to make. I mean, peeling off a tiny sheet at a time with sticky tape isn't really scalable. We can grow graphene sheets by heating up a sheet of hydrocarbons like methane until the hydrogen separates, leaving only the carbon behind, but the graphene we get from this is mostly low quality. Basically, it's hard to create a 1 atom thick sheet of anything, and it's also really hard to get a completely pure sample of anything, and here we're trying to do both. But then again, the silicon industry faced the same purity problem 50 years ago, and we eventually solved that problem with time and some money. So with some more time and some more money, I'm sure we'll do the same thing for graphene. Thanks for watching this SciShow Dose. If you'd like to help us keep exploring the frontiers of awesomeness, go to subbable.com/scishow to find out how you could become a supporter. And if you want to keep getting smarter with us, don't forget to go to youtube.com/scishow and subscribe.